systems of equations. I want to start with a really simple example, but I want to identify the system with kind of two different things. So one you would expect. So first of all, these are both straight lines in the plane, in the Cartesian plane, right? This is another straight line in the Cartesian plane. And just to be real precise, I have these lines drawn here. The green line right here, that green one, is this first one. And the blue line right here, right, is the second one. What does it mean to say you solve this? It means you find the pairs x, y that make this thing true, right? And you know that with two lines, they can intersect well, they could intersect nowhere. They could be the same line, so they could be, just lie on top of each other, or they could intersect at exactly one place, right? And clearly these two are not parallel, and so they intersect at exactly that one place right there, right? And you can see from the plot that this is the point 2 minus 1, and if you plug in 2 minus 1 here into the equations, you'll see that we get this solution here, right? So that's easy, and I'm going to look at how to solve it in just a second. I mean, this is a particularly simple one, but I also want to look at this in a different way. In fact, maybe even two different ways. So another way to look at this is to look at it as putting together two vectors, right? So it's really saying, can I find a way of taking that vector and adding this vector to y, right, and getting the vector 8 minus 2. Okay, so that's interesting because now this has a completely different picture, right? So this 2 minus 2 vector, let's see, so that's going to be the vector right here, this little black vector right there, which happens to be in the same direction as the blue line. Did not mean that to move. Okay, and minus 4 minus 2, well, that's this red vector right there. And it's in the same direction, right, as our green line is there, right? So that's this line, right, and the blue line is this line here, right? So these are two very and then what is 8 minus 2? Well, 8 minus 2 is this point b over here, so that's another vector, right there. And just to be clear, how are we doing vectors here? So the way we do vectors here is we associate them to points in the plane. Where the tail is sitting, at the origin, and the vector is coming out here to a point, and then we typically call this like x, y, like that, where this would be the x coordinate, and this would be the y coordinate over here, right? But we kind of view them as this sort of line segment with an arrow at one end, right, with a direction. And then how do we do vector addition? Well, vector addition is this nice parallelogram rule where you take, like I want to add this long black vector here to that long red vector there. But what I can basically do is take this long black vector here and just stick it right here where this one ends and follow it down and see where I end up. Or I can take this long, I can go down this long vector, black vector here, and then take this red one and just stick it right here and see where I end up, and they end up at the same place. Okay, and algebraically it works out really nice. So we have like this. If I have a vector AB and I add to it a vector CD, right? So again, the picture to have in mind is this nice parallelogram over here. This is called like the parallelogram rule or something for vector addition. But algebraically, it also works out very easy. You just add component-wise like this, right? So that's also very easy, right? So both things are very easy. Okay, so the upshot of all of this is we have two very different pictures of what the same equation is, right? So in one case, I'm looking at this as two lines intersecting. In another case, I'm looking at this as trying to find some coefficients so that when I add those two vectors together, I get this vector, right? So again, so I'm taking this black vector, I'm scaling it by some coefficient. So in this case, I'm calling that coefficient, I think it's the C1. Let's change it and see. Yeah, so it's that one. All right, so I'm scaling it by that much, and then I'm taking this vector and I'm multiplying it by something, so I'm scaling it, right? And sorry, I keep not expecting that to happen. And the result wants to be this B over here, right? So two very different pictures, right? for exactly the same thing. I will just say one other thing is once we define matrix multiplication, we could also do it like this. 8 minus 2. So now this is even another interpretation. So now I have this matrix A, and I have this vector x bar, and I have this thing I'm trying to hit over here, B. And now this is basically like a function, right? So, x bar is getting mapped or transformed to ax bar, right? And now we're saying, find the find the element of the domain that maps to B, right? So this is like trying to find a preimage of something, in the image of a function, right? So that's kind of another interpretation of the very same problem, right? Now, the same technique is used to solve all these problems. It's Gaussian elimination, right? And so that might give you a hint as to why Gaussian elimination is important. Let's just see visually that, as long as these two vectors here, this one there and that one there, are not parallel to each other, and here we are in R2, it does make sense that I can find a solution to this. And so what I can do is I can just scale. So now I'm changing the scaling on the vector. And I'm just going to bring this so that the red line right here hits that, just becomes tangent, right, to that B right there, right? And then I'm going to do the same thing here, and I'm going to bring that so that that black line just hits that point right there, right? So now I've got this little parallelogram right there, right? And now I've got this scaling, so C1 times V1, that scaling there, plus C2 times V2, that vector there, gives me exactly the point B that I'm interested in. And notice at the same time, the point here, which is sort of indicating like what's going on with the solution up here, right? So that's if I move this around, right, that kind of moves around, right? So it's giving me different values I would be getting out here. Let's see, what's it doing? It's giving me, this little point here is really just the point C1, C2, right? It's just sort of giving me the X and Y's, right? And so when I hit the right thing, then I should be getting exactly this equation. So I should be building exactly B. And so let's put this back. So let's slide this back down. All right, yeah, let's get exactly there, right? And I get that 2 minus 1 is exactly the solution I should get there. And you notice that then that coordinate right there, that 2 minus 1, just that coordinate 2 minus 1, is exactly where these two lines intersect, right? So this is a nice visualization of what's going on in R2, right? Just for the fun of it, because I have it, so you can access this. This is the notes that I have for you. I have this section. These are notes. Now this takes you over to some notes for another class that I have. And so the one I was just looking at is this one with the 2D version, right? And so we're looking at exactly this problem done here. You can look at the same thing in 3D. If you just consider the system of equations, let's say just consider this system of equations, right? Then each equation corresponds to a plane, okay? And so here we're intersecting three planes, right? And you would expect that intersection to look like a point. Let's see if this shows up this small. Yeah, it does. Okay, so here's the three planes that were right there, and there's that point. So I'll let you play with this and verify that these three planes are exactly the planes there. The blue lines here are where so this blue line running this way is where this yellow plane and this pink plane are intersecting. And this blue line running this way is where let's see, it's actually hard for me to see here. I think it's the blue plane and the red plane are intersecting. But anyway, you see that those lines that are intersections of planes also intersect at the point where all the planes intersect, right? So the intuition is pretty clear. You can hold up pieces of paper or something if you want to get that same intuition. Unlike the two-dimensional case, it's harder to draw these on the same plot. So that's that. The corresponding vector interpretation would be this one. Let's see if this one will show up. Yeah, okay, so this one's showing up. So there's the B that I'm interested in getting. Here's the direction of my three vectors. So again, let's go back and look at this, right? So here's the system, right? So instead of writing it as a system, I could take the coefficients there and write that as a vector, and then plus this vector plus that vector and equals to that vector, right? And so then the x, y, and z just become how I'm scaling those vectors to make this equation, this single vector equation, true, right? So here's a system of three equations. This is one equation. right? Just involving vectors instead of just variables, right? So that's a change in perspective in some sense, right? And so this is doing exactly that, right? So we're doing the same sort of thing. The plane that's drawn here is the plane spanned by v2 and v1, right? And so the first thing I try to do is sort of find what you need to do to get, so if I take B and I project it in this direction onto that plane, I get that point there. And then I want to see how to get that point back from those two vectors. So I'm sort of dropping back into a two-dimensional case on the plane spanned by those two things. And then once I've done that, so I've got the point A, and then I can just sort of stick this vector back on there, right? And I get that. So these are all techniques you would learn in a linear algebra class. But the point here is just these two different interpretations of what a system of equations might be visualized as, right? And so this is just kind of visualizing systems of equations. Okay, so that's sort of maybe, I don't know, the philosophy part. So let's just get rid of this. When we actually go to solving them, we're going to focus on the matrix version, and then this version appears. Let me start with this version. What can we do with equations if we have some equations like this? Well, we can do lots of things. We could divide, you could multiply any equation by a non-zero scalar. That doesn't change the system, right? It doesn't change the solutions. I could, so let me just sort of spell these out, and I'm not sure what, didn't really think about this, like what order I want to put these in. Let me see if I say this in these notes, because I didn't think about this. I'm not even sure I wrote it here. Nope, not there. Let me look one more place. I want to get the same order, but I just have to. Here, elementary matrices. Okay, yeah. So there's three operations I can do. I just want to make a matchup with some stuff later on. So there's type 1 operation. Is to swap to, in this case, swap two equations. This is actually important for understanding some of the stuff that goes on. But clearly, if I swap these two equations here, or if I had a bigger system, I just swapped any two equations, I do not change the solution set, right? I mean, the set of the same, solution still works, right? The type 2 ones, operations, are to just take a particular equation and multiply it by a non-zero. Now, if I multiply by 0, of course, I just kill all the information in that equation. So that can't work. But I can multiply it by any non-zero scalar, right? So just replace an equation, an equation by a non-zero multiple of itself. Okay, and then there's one more important one that we'll actually use, I think, even for this one. So type 3, and actually type 3 are the ones we want to use most of the time. I mean, in this class, we won't sort of talk about why, but mostly we want to use these. And so what I want to do is I want to take a scale, so add a scalar multiple of, say, row I. I could just call it row sub I, or equation sub I, to row sub j, and replace the result with row j, or equation j, right? So I'm saying row because I'm thinking already matrix operators later. But those are the three things. This one's a little less clear that you don't change the solutions. But if you think about it, if I have something that solves this, I could always undo this action here, and I would, and I'd get back to my original set. So the set of x and y's that solve these things are the same. And this will be clear when we do an example. We'll just do this silly example here. Okay, but those are called the elementary operations on systems of equations, and the point is that when we perform these elementary operations, we do not change the solution set. Okay. Now we're going to interpret that with respect to matrices later, so it's important just to keep that in mind. Okay. So let's actually solve this system using this kind of thing. So I'm going to do exactly that type 3 operation. So I'm going to take, let's call this equation 1 and equation 2, right? And what I'm going to do is I'm going to take equation 1 plus equation 2. So 1 times equation 1 plus equation 2, and I'm going to replace equation 2. Right, so I'm going to get a new system. So I didn't do anything to equation 1. Whoops. Minus 4y equals 8. Equation 2, I did this thing. I added equation 1 to equation 2, and I'm going to replace equation 2. So I add these, right? So 2x minus 2x is 0x, so that goes away. Minus 4 plus minus, so minus 6y, right? And then 8 minus 2, right, is just 6. Right, so I'm just adding those two. So this is still equation 1. I didn't change that, right? But now this is maybe equation 2 prime. Okay, and the claim above was just that the set of solutions for this and the set of solutions for that are exactly the same, right? We didn't change the set of solutions there. The same xy's work here that work there. And again, that's clear because if an xy works here and I can just do this operation, then it will work here. And if an xy works here, I can just undo this operation, right? So I can start with this guy and subtract off an equation 1, right? And then replace equation 2 to get back to that one, right? So I can get from there to there and get from there to there, and the same solutions will work, right? So that's kind of clear. Now, once I've done this, I'm just sort of throwing a bunch of stuff in here together. This has a particularly nice form. This is kind of a triangular matrix like that. And once we get to a triangular matrix, we use what's called back substitution, right? So here I've got minus 6y equals minus 6. So I can just now solve for y, right? Y equals minus 1, right? And once I have y equals minus 1, I can plug that in here. So I get 2x minus 4 times minus 1 equals 8, right? And so this gives me 2x equals 8 minus, so this turns into 4, and then when I subtract, it's going to become minus 4, so minus 4 is equal to 4, right? So x is equal to 2. And that's exactly the solution we saw, right? So this pair 2 minus 1 is exactly the solution we saw in the picture before. Okay, so that's sort of in simple the way this works, right? So that there we are doing this stuff with equations, okay? Now what I want to do is take this and say, okay, well, we could have just written this equation as a matrix, all right? And in particular, we can write it as an augmented matrix. So let me sort of throw that in there. So I can take this thing and I can just sort of forget about the x and y, except their positions, right? So sort of this is where x's go, this is where y's go. And I can have 2 minus 2 minus 4 minus 2, and I kind of augment it. And sometimes you just draw a line like that to say 8 minus 2, all right? And now what I'm going to do is I'm going to do exactly the same kind of thing, but I'm going to do the operations on the rows, right? So here I'm going to say, I'm going to take row 1 plus row 2 and replace row 2, right? And so that's going to give me a new matrix, which will be 2 minus 4, 8. I didn't do anything to the top row. And then here I'm going to get 0 minus 6, 6, right? Just as before. With the equations, right? So now what is this, what system does it, so we could go back now and just, so here we have a matrix which has this nice form. This one's called upper triangular, but more generally it's called an echelon form, right? And once we get to an echelon form, we stop with this part of the matrix stuff and then just go back into back substitution, right? So once I'm here, I can sort of re-extract the system of equations corresponding to this matrix, right? And I get 2x minus 4y equals 8, and I get minus 6y equals 6, right? And then I start using back substitution. So y is equal to minus 1, all right? This is going to become 2x minus 4 minus 1, because that's what y is now, is equal to 8, all right? And you just work your way backwards and solve, right? Just like before, okay? Good. Okay, so that's sort of the basics of this. Let's do a slightly bigger example to just see, just to see a bigger example. So let's actually do this 3x3 version here. So let me just clear all this. Okay, so I take this system, I'm going to put it into a matrix, right? So it's going to be 3, 2, 1, 6. By the way, later on I have a MATLAB section where I'm going to show you how to do all this in MATLAB too. 4 minus 2 minus 5. Even in simple cases, it's easy to make mistakes, like because maybe I can't read that that's a minus 5. And then 1, 2, minus 3, and 0. Okay. And what I want to do is I want to use my operations to reduce this to an upper triangular matrix, or what we'll later define as an echelon matrix. Here, it might be nice to have the one up top. So there is a very specific way I want to do this. I want to work from top left, sort of down. So I want to kill every non-zero thing here below the first thing. So this first thing is going to be called a pivot. It's really useful for the pivot to be a 1. So the first thing I'll do is just swap. That was one of the things I could do. That's one of my elementary row operations. So swap row 1 and row 3. All right, so then I'll get this new matrix, which is 1, 2, minus 3, 0. And then this one stays the same, 4, minus 2, minus 5, minus 3. And this one becomes 3, 2, 1, 6. Okay. And now I'm going to just apply a type 3 operation. I'm going to actually do it twice. So as long as you're doing 2 type 3 operations on, to get rid of these same 2 things, we can do them simultaneously. So I can use this. So now what I want to do, I want to use this thing here, which is called the pivot. And so that's never going to change again. I want to use it to kill the stuff below there. So I want to get rid of those guys, right? And so I'm going to do row 2, or let's say, I'll say it like this: row 2 minus 4 row 1 is going to replace row 2. That's a type 3 operation, right? And then row 3 minus 3 row 1 is going to replace row 3, right? So that's going to be what I do next. Okay, so then we have to do that. Now here's where you can start making silly mistakes, and who knows, maybe I'll do that for you. So here, 1, 2, minus 3, 0. That's just going to stay. Nothing's happening there. And of course, these are going to become 0, so I can do that safely. Now I've got minus 2. I'm multiplying this by 4, so that becomes 8. And then I'm subtracting, so I get minus 10. Right, I have minus 5, multiplying this by 4, so that becomes minus 12, but I'm subtracting, right? So that becomes 7, minus 5 plus 7, right? And now 0, 0, so nothing happens there, right? And then here, I'm subtracting off 3 of these, so I have 2, minus 6, so that's minus 4, whoops. And then I have 1, plus 9, so that's 10, right? And then this is going to stay 6. Hopefully I did that right. I mean, it's because I'm multiplying this by 3, so I get minus 9, but then I'm subtracting that, right? So it becomes 1 plus 9, right? So I get that. And now I want to get rid of, now what I want to do, so like there's the first pivot, and we've taken care of that. Now I want to take the next thing, which is a pivot. Okay, so this is still not what we're going to call echelon. It's definitely not upper triangular because I still have zeros in this lower triangle. But it's also not echelon form yet because I have here a place where there's a pivot first non-zero thing, and there's something non-zero below it, right? So I'm going to take this pivot here. Now I'm going to get rid of that thing there, okay? And, I could divide out this one to make it easier, right? And, and swap again or something like that. But we may as well just do this in sort of a general sense too. What do I do to minus 10 to get it equal to 4, right? To get it equal to minus 4, well, I can take, I can just multiply this thing by, minus 4 over 10, right? So that's going to give me whatever it gives me, right? Row 2 plus row 3, right? And that's going to replace row 3, right? So let's just think about what that actually gives us. Okay, so 1, 2, minus 3, 0 here, right? 0. I'm not changing this one again, so minus 10, 7, minus 3, 0. So now what happens here? So what I said here is I'm going to take minus 10. I'm going to multiply it by minus 4 over minus 10. Sorry, minus 4 over 10 is what I said. Actually, let's do let's multiply by -4 over -10. No, let's do it like this. -4 over 10, right? Which is what I said here, right? So this will give me 4, right? So that gives me 4, right? And so if I add, that cancels. That's good, right? And then what do I get here? So now I'm going to do -4 over 10 times 7, right? Plus 10, right? So like that. Okay, so this is a little bit more of a pain. So this is -2 over 5 times 7 plus 10, right? So this is -14 over 5 plus 50 over 5. Okay, so this is 36 over 5. All right, so we get that kind of messy fraction, but that's all right. We're not afraid of fractions. 36 over 5. And finally, let me see what I get with my -3. This may be a good place to like also, whoops, this was 36 over 5, I think. All right, and so then I have -3. Whoops, I erased what I was multiplying by, so it was -4 over 10, right? Plus 6, right? That's what I'm doing there. So now I've got 12 over 10 plus 6, which is 6 over 5, plus 30 over 5. Oh, that kind of worked out nice, didn't it? So this is 36 over 5. Okay. Now we've got this upper triangular form, right? So lower triangle is all 0, and we've got that. And now we just start doing back substitution again, right? So I mean, what does this first equation turn into? It turns into 36 over 5, z equals 36 over 5. So wow, that's nice. That means z is 1, right? And then this next one turns into -10y plus 7z, but z is 1, right, equals -3, right? So this turns into -10y equals -10, right? So y equals 1. That's nice. Okay, you might think I picked it so that this happened, right? And then the last one turns into that. So x plus 2 times 1 minus 3 times 1, right, is equal to 0, right? And you can look at that and see easily that x equals 1, right? So like that. Good. Okay, so that's sort of a more general case, right? So again, you use the rules for Gaussian elimination to get to a matrix, which is, I mean, right now I'm saying upper triangular, but really echelon form, and then use back substitution to finish your solutions. And when you implement algorithms to do this, essentially you do something like this. So back substitution is really, really fast. Stuff up here is pretty fast, but not quite as fast as back substitution. So you sort of do things in that order. And this video is going to stop. So I'm going to continue a little bit in the next video.